Hi, and welcome to the Allplane Podcast, here talking with the movers and shakers that are redefining the future of commercial aviation. And as usual, before I introduce today's guest, let me remind you that all previous episodes of this podcast, as well as many other aviation stories, are available on the Allplane website. That's Allplane.tv, Allplane.tv. Our guest today is Helmut Mayer, an aviation entrepreneur working on a very special project to decarbonize air travel. Aviation H2 is an Australian startup that aims to power aircraft with ammonia. We could consider this as a subset of the hydrogen economy that so many headlines is generating lately. There are quite a few entrepreneurs out there experimenting with hydrogen in different forms as a fuel for aviation, but what is not so common is to use hydrogen in ammonia form. Actually, the chemical formula is NH3. Ammonia is typically used to make fertilizers, and it actually has a history in aviation as well. In the 1960s, it powered the North American X-15, which still today is the fastest manned powered aircraft ever to fly. Well, some people would say it's a rocket, but yeah, still that record still stands. Helmut and his team at Aviation H2 think that it's actually time to look again at ammonia as a potential fuel for aviation, for aircraft. They have secured a number of engines and a whole Dassault Falcon 50 executive jet to start testing this concept in the coming months. So let's travel virtually to Australia to listen to what Helmut Mayer, the co-founder and director of Aviation H2, has to say about this technology, the status of this project, and the prospects of ammonia becoming the aviation fuel of the future. Hello, Helmut. How are you?
Hello, Miguel. I'm very well, thank you.
Good afternoon to you, because you are a few hours ahead of me in Australia, right?
Yes, just a few. So it's about 5 o'clock in the evening here.
Yeah. So it's about, I think, 8 hours difference from I'm based in Barcelona at the moment recording this. Yeah, I really wanted to speak with you because I came across your very interesting project, Aviation H2, which is basically the project to fly an aircraft using liquid ammonia. But before we get into the details, I just wanted to basically, like every guest, to ask you to introduce yourself and a little bit of give us a little bit of your background and basically how did you end up working in this type of projects?
Yes, thank you, Miguel. So I've been an engineer for a long time, although I did start out life as a pilot. So after I left school, got my pilot's license, flew commercially in Australia for about 10 years or so. Struggled to get into the airlines, struggled to get my hours up. We had a pilot strike, and fate took me down the path of studying engineering. I studied aerospace engineering at the time because it was very interesting, together in a double degree with psychology because it was very interesting. And I applied the engineering in the mining field. My father had a design office for mining machines for the continuous handling of bulk materials. And as remarkable as it seems, but there's a lot of similarity between the two fields. There's a heavy focus on structures and mechanics, and that helped me a great deal to have studied aerospace engineering and to be able to apply that in that other field. And so for many years, I did actually work in that industry, designing machines, designing complex ship loaders, for example, reclaimers, stackers, from ground up, mechanically, structurally, and through to the safety functionality, which I then signed off. And so I got a lot of experience in applying design process and using multiple disciplines to deliver complex designs into the field in a short time. Mm-hmm. And in all that time, I kept up my interest in aviation, and I asked a lot of questions about it. I formed a partnership with my brother Christoph to develop this engineering business. And together we've been speaking about entering the decarbonization industry for some time. Like 10 years ago, we started talking about this.
Well, that's early on, because right now there's a lot of talk about this, but 10 years ago, it was really, not even 10 years ago, I remember starting to look into what was going on in this space about 2-3 years ago when it was much smaller than it is now.
Yes, 100%. And really, we should have been where we are now. We should have been 10 years ago. I mean, the climate warming has been a hot topic for decades. It's not new. We've known about the problem for some time. And Christopher and I knew that it would become urgent at some point, and we knew that we had to act. Everyone in the world has to act locally, globally, everywhere. And so we talked about how to apply our engineering skills to the problem to make our contribution to that, and that included various endeavors. We did some research into automation of drones. We did some research into, and that was my background, but we also did some research into the production of carbon-free energy, transportable energy, so hydrogen, basically, and a number of other derivatives of that. We spoke with investors about it. There was a few things that went backwards and forwards. There wasn't quite enough momentum in that. And then recently, the opportunity arose to work with Liberty Energy Capital to come up with a project to make an aircraft fly on carbon-free fuel. And so we were ready to join that partnership and apply our engineering skills and our knowledge that we've gained over the years to that specific problem. And
sorry, Energy Capital is a partner company, is an investing company.
The company Aviation H2 is a partnership among a number of people and groups, and we are the engineering side of things, and then the others are the capital side of things.
Okay.
So we work together to promote, to market, to raise capital, to deliver the engineering, and all those things are necessary to deliver a project like this. Neither Christoph nor I nor our other partner Greg, who is in the aviation space, none of us have any illusions that the project like this can't be done, or that it could possibly be done without close attention to the commercial side of things. It's not sustainable to try and do this without using capital, without using finance, without delivering wealth, productivity, all those issues. So we're working together to make all those things happen for the project. It's very important that we work towards a way of doing this commercially in the future.
Yeah.
So that's what we're doing. I mean, right now there's a lot of focus on getting the technology going, and that has to be. It's new. We set ourselves a mandate to achieve an outcome, and the first thing we did was to study existing technologies very carefully to understand what we could and could not use off the shelf. And we controlled for development very tightly. So we analyzed what technologies, what steps we had to develop ourselves, what research we had to do, and we minimized that by using existing technologies if we possibly could, so that we don't end up having to spend years and decades trying to develop a new thing that's too far away. That's the role of other people like Boeing and Airbus. That's not our role.
So you basically chose this technology using liquid ammonia, and you plan to basically modify some engines and fit them into an existing airframe, right? I've seen on your website I've seen some pictures of an executive jet, and I've seen also one of your partners is an operator of Dassault Falcon executive jet. So can you tell us a bit more about how you plan to do this? Because your company isn't what I would say like the hydrogen economy, but you have this very specific approach, which is using liquid ammonia, which is, I will ask you now to explain us a little bit more about the chemistry of this, but basically it's quite a novel way of using this hydrogen in aviation.
Well,
not novel maybe, because I know there are some historical precedents, but let's say it's a very particular way to do it, right?
So let's go back a step.
Yeah.
So we did this study for our purpose, right? So we didn't say, in general, we think this is the way aviation is going to go. We said, these are the things that we can do and need to do to be able to achieve flight with carbon-free fuel by this time. And what we did is we analyzed a number of paths of doing this. So power paths, we call them. And the power path is the entire system of fueling the aircraft, storing the fuel on the aircraft, transferring the fuel from the fuel storage system to the power generation system, and then transferring the power to the thrust generation system, and then defueling the aircraft at the end of the flight. Okay, so it's the entire system. It's not just the engine, it's the fuel system, it's the engine, it's the fuel storage system. And we had a look at, for each of those power paths, and there was a number of them there. So we looked at battery electric, we looked at hybrid methods, we looked at liquid hydrogen, we looked at gaseous hydrogen, we looked at ammonia, liquid ammonia, gaseous ammonia. We looked at various amines. So there are different methods of storing hydrogen again. And we had to look at what it would take to modify an aircraft for a 1 hour flight profile, and whether we could fit it into the weight budget that we had available on the existing aircraft to make that happen. Okay. Yeah. And we selected a specific aircraft, and we selected a specific flight profile, and then we went and did the work to evaluate exactly those things. So it's weight, it's volume, it's energy. And the two most favorable systems were liquid hydrogen and ammonia.
And what can you tell us about this liquid ammonia, and how is it different from the liquid hydrogen? Can you tell us a bit more about the chemistry of how this works?
Yes, so liquid ammonia is a carrier of hydrogen. That's the best way to say it. So Aviation H2, although we're using liquid ammonia, we are using hydrogen because ammonia is a carrier of hydrogen. Mm-hmm. And H3, right? That's ammonia. Yeah. In fact, one of the curious statistics is that if you take a cubic meter of ammonia, mm-hmm. you can fit more hydrogen into that cubic meter than if you took a cubic meter of pure hydrogen.
Yeah, actually, just a parenthesis here. I think I'm not an expert. I don't claim to be an expert in this, but I think ammonia is one of the ways that exists to take hydrogen and basically transport it from one place to another, right? So you can produce hydrogen in one place, and by converting it into ammonia, you can then move it. I was about to say easily. I don't know if easily is the word, but you can. Well, there are technologies that allow you to do it. Yeah.
Much more easily. You know, like hydrogen is either going to be highly pressurized as a mm-hmm. gas, mm-hmm. and we're talking on an aircraft, we would have to select 700 bar of pressure. Mm-hmm. That's a lot of pressure for a gas. That's a lot mm-hmm. of strain energy in that gas. Or you have to carry it cryogenically, meaning at minus 253 degrees C. That's mm-hmm. very cold. The tank system to do that are quite complex. And so then we're thinking about how to fuel and refuel and defuel the aircraft. The thing with cryogenic hydrogen, liquid hydrogen, which is the path that some people have gone, is you need to have a liquefier at the airport, and you need to load the fuel onto the aircraft using cassettes. And then at the end of the flight, you still have reserves left. You don't want to release them into the atmosphere. That would not be sustainable. So you need to take those cassettes out again, put the fuel back into the liquefier. So you have a fueling and defueling operation for each flight.
Yeah. But what about ammonia? How do you store it? What sort of requirements? Yeah.
So liquid ammonia at the moment is stored industrially at industrial quantities, very much like liquid petroleum gas, so the LPG. Uh-huh. It's got a tank and it's slightly pressurized. So slightly meaning 10 bar, 11 bar or so. We are actually going to pressurize a little bit more. We've selected 35 bar as the pressurization. We may need less after experimentation. But the reason we did that is because we need to keep the ammonia liquid under a great range of atmospheric conditions, including on the tarmac in the summer heat with very hot temperatures under the wing. Mm-hmm. Okay, so we're using a relatively high pressure, but it's actually very moderate when compared to gaseous hydrogen. 35 bar is entirely manageable.
What are the volumes? Because one of the main issues with hydrogen is that people that have seen these renderings of potentially new designs for hydrogen power aircraft is that you need a lot of space for the tanks to store them. How does it work with ammonia? Do you also need these huge tanks fitted somehow in the plane?
You need, for the same amount of chemical energy stored, you need about 2.6 times the volume of Jet A.
Mm-hmm.
Right?
Okay.
It's a lot, right? So if you now say, okay, we'll build a fuel system that has the same amount of Jet A, you've got a bit over a third of the range of the aircraft, right? That's problematic. The other thing that's happened though is when you have a look at the amount of chemical energy that's stored on a jet like the Falcon 50 or an Eclipse 550 or whatever, it's a lot more than what you actually use to convert to thrust. And I'm talking about 10 times more. I'm talking about the overall system efficiency being pretty low, and we've seen cases where it's 0.1. And this is going to be a problem for all of the alternative fuels, because the same problem applies to hydrogen. Hydrogen's got a very high energy density, but it's very light, and it has a very low density, and so you need a lot of volume.
Yeah.
And it's not just weight, it's also volume. With a hydrogen, you need a lot of volume, but you still need a lot of weight, because the tanks that you need to put in place to carry the fuel are heavy. So the storage system is still heavy, and you still have the same problem. So there is a need to improve efficiency to get the range back. There's no question about that. That will be the case whether you use hydrogen or whether you use ammonia or something else. And one of the things that comes out when you study it in this much detail is that, there's a good reason why we used Jet A1 in the past. It's very convenient. It is incredibly convenient, actually.
Yeah.
But the thing is, it's no longer acceptable. We cannot continue to blow carbon into the air beyond 2050. We just can't do it. We need to take as much out as we put in, at least.
Indeed.
Probably less.
So basically, the system that you propose, well, you're developing the system not just to store this ammonia, but also you're going to be using it directly as a fuel. So burning this ammonia as a propellant for the aircraft. Technically, what does this involve? Because you're going to use an airframe that exists. You're going to feed this system into the airframe. And what you need to do here is first find a solution for, obviously, the storage, then find a way for the engine, which I assume is an existing engine. I read in your website that you recently procured some engines to do some testing. So you're going to retrofit an existing engine so that it can work by burning ammonia instead of jet fuel. So how does this work? You don't need to go too much into the technical detail maybe, but just to get an idea of how this whole system will work, and what is the part that you are developing with your own technology? Because obviously the airframe you're procuring and in the market, whether through your partners, and then the jet engines you're retrofitting also an existing jet engine, right?
Yes. So the first thing to note about this is that when you burn ammonia at the right fuel air mixture, and it's called the stoichiometric mixture, it has a very similar, that's just slightly higher burn temperature compared with burning Jet A or kerosene at the correct mixture for the kerosene. And what that means is, provided that we work with the correct mixture, we'll have a very similar temperature in the combustion chamber, and that's what provides the thrust. It's the step in temperature that provides you with the energy to drive the compressor and the fan. And so what we need to do is we need to convert the fuel system to feed the corrected amount of liquid fuel into the combustion chamber to give us the same burn energy. And because they're very similar burns, that will be relatively straightforward. Where the difficulty lies is that the ammonia flame propagates slower than the kerosene flame. And so,
sorry, what does it mean that it gets slower? What does it mean in practical terms?
So it burns less fast back towards where the air and the fuel are coming from. So you can, if you blow too much air through the combustion chamber, it'll blow the flame out with it. So the flame can't keep up with the amount of fuel and air that's coming through the combustion chamber.
But in terms of practical performance, what is the implication?
So what that means is that we need to modify the way we are operating the combustion chamber to make sure that the flame, the ammonia flame, burns stably throughout the flight. That was one of the key questions that we had. However, we were able to identify and then build on research developments overseas that addressed exactly that question. And these research papers have provided the sort of parameters we need to think about and work with to get the flame to burn stably in the combustion chamber of the jet. And that's our biggest research part for the conversion of the engines, to make sure that the flame burns correctly.
Okay, and what sort of performance are you then expecting to achieve, provided that everything goes according to plan?
We expect to achieve matching performance, apart from fuel flows. Like the quantity of fuel going through the engine will be higher.
So
But delivery of thrust will be the same.
The same as in jet fuel, conventional jet fuel. Mm-hmm. And are there any side effects of this
Yes.
that you want to avoid? I'm just thinking in terms of emissions, and not just CO2, but other type of gases that might be produced. What is like the byproduct of this process?
So there's two issues that we need to deal with. One of them is, believe it or not, vapor trails. It turns out that vapor trails are actually a pretty substantial part of global warming arising from aviation.
Mm-hmm.
And when you're burning a hydrogen type fuel, you're ejecting more water out the back, which means the conditions for vapor trails will be present more often than with Jet A1. And that means that the vapor trails will actually contribute to global warming. However, work has already been done outside of our work, and we're just taking that up, is that there are ways of managing the vapor trails and the opportunities for them to arise that we can use to avoid that problem, right? So we're not putting any research into that. We're leaning on other people's research that's already going on and that already has borne some results. Everybody will be doing that. So the emissions, vapor trail emissions, will be dealt with quite confidently. The other one is nitrous oxides emissions. Now, if you take any fuel and burn it in the presence of air, which has a lot of nitrogen in it, you end up with nitrous oxides in the exhaust pipe. The hotter the burn and the longer the burn is at that heat, the bigger the nitrous oxides emissions. Now, I've already said, we might recall that the burn temperature is very similar, and so the nitrous oxide emissions between the jet engines and the ammonia engines will also be similar, right? And with the hydrogen as well. The hydrogen will also have those issues. In fact, the hydrogen may have more issues because it burns hotter, quite a bit hotter. Like we're talking 20% hotter. So the way all the engines, including Jet A1 normal engines and SAFs, which is sustainable aviation fuels, they all have to deal with this issue because it's relatively new, but it has become a legalized requirement now to get rid of the nitrous oxides substantially. Now, the beauty about ammonia is we can use the ammonia to create a second burn in the tailpipe to break down those nitrous oxides. If we take a hydrogen plane flying, we have to have hydrogen in the tanks to fly the hydrogen, and then we have to have more tanks with ammonia to break down the nitrous oxides.
Ammonia, I read that it was used by some experimental aircraft back in the 1950s, but it hasn't really been used or even experimented with during all this time. So why do you think is the case? I mean, with all the talk that is going on about finding novel ways to deal with carbon emissions and all that, why are we not seeing more activity in the field of ammonia research? Let's put it this way.
Well, this is an interesting question. So in the 50s, they did try ammonia and various other methods, but it fell by the wayside because Jet A is just so convenient. As already said, it really is quite extraordinary how convenient Jet A is.
Yeah,
and that was the detriment of ammonia at that time. So now we're looking for replacements for Jet A, and ammonia is coming back. Now, like you say, there's a lot of people have elected to use liquid hydrogen instead of ammonia, but that, I mean, I have spoken with the people who've made that decision, and they said, well, we're taking a bit of a punt, right? And it's very early days. And when you look at the images that shows how this might work, you can actually see that the cassettes of liquid hydrogen that they need to fit on board the plane won't actually fit. What will be required is they will build new planes that are built around the liquid nitrogen tanks.
Yeah,
that's pretty substantial.
Yeah,
we need to deal with those problems.
Yeah.
So it isn't yet a complete given. And on several occasions, I've actually spoken with people and said, tell me, why are you using ammonia? Because we think it should be ammonia, but everyone else is choosing liquid hydrogen. Cool. Well, look, we're taking a punt. We don't actually really know yet exactly how this is going to go. But what I can say, for our purpose at this time, the ammonia is by far the easiest way of doing things. And I said before, liquid nitrogen and ammonia were very close together in the weight and volume stakes, but in the usage stakes, the ammonia is much better.
What about the whole supply chain? Because that's another issue with hydrogen, is how to get all the infrastructure in place. I guess ammonia has a global supply chain, but I don't know how granular that is in terms of being able to get to the airports, because obviously now ammonia is being used for other things. So how difficult or how easy it is to take it to the aviation space?
So what's going to happen here is that the existing industrial infrastructure needs to be increased by a factor of 10. Right? But the thing is, the industrial infrastructure exists, the technology exists, and then multiplying something by 10 isn't such a big deal when you think about what's at stake here.
Sorry, when you say multiply by 10, are you referring to the production capacity?
Yeah, the volume of ammonia that needs to be delivered to market.
So factor of 10 would be to achieve what goal, what type of volume?
This is in the hypothetical scenario that the aviation industry changes from Jet A to...
Okay, so to replace Jet A completely. Okay.
Yeah.
Okay, that's tall order. But
now, say let's think about an airport in the middle of Africa. Will they put in an ammonia tank, which is a bit like an LPG tank, or will they put in a liquid hydrogen tank? Right now, obviously, if Qantas rings up and says we need to land in your airfield and we need to have liquid hydrogen, they're going to have to find a way of getting liquid hydrogen there. But if they have a choice, it's going to be a lot easier to put in ammonia, a lot easier.
Yeah.
Because a liquefaction plant is small. That's high technology. That's not a trivial task.
You wouldn't need to freeze it to minus 253 degrees, I guess, but still, would you need to build infrastructure from scratch? So there's going to be lots of piping and tanks and other stuff that will need to be built, or could it potentially use the existing one?
Sorry, are you talking about the ammonia or the liquid hydrogen?
Ammonia. I mean, can it use existing physical infrastructure, or it would need to be built from scratch? Well,
probably not. It's a bit like when you introduced LPG into petrol stations. Petrol stations had to come up with a bit of real estate and the piping, put it in a tank.
Okay.
Above ground. It had to be above ground. The petrol tanks were underground, still are. But you got a big tank that's above ground, right? So you have to get a spot, put some concrete down, run some pipes to the bowsers, build a tank.
Okay.
Now for the airport, of course, it needs to be a lot bigger than for a petrol station, but still it's a lot easier to do that than to build a liquefier for the airport.
Yeah. And what about the market for ammonia at the moment? Is it a traded commodity? Is there a global market for it that is actively traded on exchanges or something like that?
That's a good question. I don't actually know that. Don't know.
But
we're ringing up the local supplier and saying, "Can we have some ammonia, please?" And they say, "Yeah, sure, no problem."
No, definitely there should be a global market for it with like sellers and takers, but I just don't know how standardized it is, like other commodities where you would have like futures and options and trading all around the clock,
Almost certainly, in the process of multiplying the existing industry by a factor of 10 within 15 years, that will happen. It will be a global commodity.
Yeah.
It will be traded on stock markets.
No, definitely at the scale. Yeah. If it gets to scale, for sure.
Contracts, not. It'll have to scale. Yeah.
So tell me a bit more about the plane. You are planning to use a Falcon jet, or that's just something that it's kind of tentative at the moment?
We have decided on the Falcon 50, and there are some very specific reasons for that. Our original study was done on an Eclipse 550, which is a very large jet, new class of aircraft. There was a couple of issues with that in the end. It suited our purpose for doing the calculations, and we still have it in the documents. But we've also adjusted those calculations for the Falcon 50 now. So we know what the step is. The problem with the Eclipse was it's a new type of aircraft. Although there was a type certification for a precedent like the Eclipse 500 in Australia, if we're going to use Eclipse 550, we would have had to get a type rating in Australia. We'd have had to get training for mechanical personnel, training for all sorts of personnel to try and get this thing to fly in Australia. Pilots, operating certificate, everything. And that would have been time consuming and costly. The other problem is because the very large jets are built for the purpose of being a small transport for people, they don't have much weight overhead. So our weight balance was very tight.
Okay.
And so when we then said, okay, let's have a look at alternatives, one of the suggestions was the Falcon 50. And the reason for the Falcon 50, it's a much bigger plane. It's got engines that are 4 times the size, and there's 3 of them instead of 2. But you can buy one. They're readily available. They're well known in the Australian marketplace. The skills are in Australia. We can buy one that's near the end of its life. It's just got just enough life left for our purposes, which is to test these principles and demonstrate the technology. And so the cost came right down. Yeah. So the Falcon 50, we were able to use an older plane that was nearly out of time, but had enough time on it for us to work with it. And so we could buy cheap engines, and for testing, and the hourly flight costs would reduce. And so there was a lot of benefit to be had. Even the cost ended up being about the same, but we're using a much bigger airplane. The big benefit was the fact that we had a much better weight budget to work with, much better. And we've got 3 engines, and it's got enough thrust in those engines. So the plane is actually certified in Australia to take off and fly on 2 engines for certain purposes.
Okay.
And we'll be able to use those purposes in our experimental flights. So what we can do is we can modify one engine. We can take the plane flying out of Angstown Airport, which is close to lots of built-up areas where you normally can't fly an experimental aircraft. We'll then fly to areas where it is safe to test things, and we can start testing the engine. And when we're done, cut it down and fly it back. So that's a big benefit for the program.
So is there where you are right now in this project? You procured this aircraft? Is this already being worked on?
We have people in the field looking for suitable aircraft. But before we actually buy it, we will demonstrate that we can control the fuel burn correctly.
Okay, because I read on your website that you have recently got 3 engines for testing, right? Those are separate?
Yes, we're in the process of getting them. It'll be some time before we actually get them into our workshop. Because one thing that we'll do is before we actually get the engines to our workshop, we will have them separated. We'll have a hot section inspection, and we will analyze what the pre-existing condition is of the turbines. Okay. So that we know afterwards what the damage is that we're causing.
But first you're going to be testing this engine separately on the ground, right? Without the airframe, and if everything goes as expected, then you would fit those engines in the plane. Is that right?
Yeah. So the way this program is planned to run is the first step in our test cell is to actually test the flame, and then we'll fine tune our design of the fuel system, and then the refined design will go into a test engine, and the test engine will then be fired, and we'll know that we can make the flame burn correctly. Then we'll proceed with purchasing a plane. But at the same time, we'll continue to do our testing program for the engine because we have to characterize it fully. Okay. So that'll take some time. But we can start, once we know that the flame burns correctly, we can then start the design of the modification of the aircraft and buy the aircraft.
Okay. And what sort of engines are those? Where did you get them from?
They're the Garrett, now Honeywell, TFE 731s, -3.
Okay.
-3 is the Falcon 50. They've been updated for the more recent Falcons, but the one that we're working on is the Falcon 50 engines.
And what's the time frame for your project, and what are the expected milestones in the near future?
So the next milestone is to have the flame burn on ammonia in a tube. So that's not a jet engine. That's a tube that we construct so that we can measure the various parameters
Uh-huh.
without having to deal with the complexity of the combustion chamber and the turbines.
But what is the time frame? What like if we were to take a calendar for the next few years, what would be the approximate? I know that can be a bit tricky because obviously many of these things need to be tested, but what would be the approximate time frame that you are looking at?
So we expect for the engines to be running in the test cell probably in 2 or 3 months' time, so say July, August, and then we'll start the process of designing the modification for the plane and making the plane modifications. So the first flight of the or the first engine burn, let's say, on the aircraft will happen early in 2023.
Oh, that's quite soon.
Yes, and then by the middle of 2023, the plan is to have it running. Now, to have the plane flying, right, on one engine, and depending on how the timeline goes, we'll have to have one running with all 3 engines on ammonia by maybe the end of 2023. But the key milestone is one engine in flight operating for a 1-hour flight profile, which includes taxi, takeoff, climb, cruise, descent, circling, landing, and taxiing back. That's the mandate, and that's planned for the second half of 2023.
Okay, so let's assume everything goes as expected. What are the bigger plans? Because this technology, can you then scale it? Can you then license it to other OEMs? What's the business plan behind this on the long term?
So the business plan is to create 2 business streams. One is the modification of existing aircraft so that people can fly their planes on carbon-free fuel. And so what that requires is that we go through a certification process, which happens after the demonstration. So that can take some time. But while we're working on the demonstration, we are developing the certification plan together with the authorities, CASA, maybe even FAA. It may have to be the FAA. And that'll be for one engine and airframe combination. And then we'll have to do, for other airframe and engine combinations, we'll have to do other certification plans. But the subsequent ones will be easier, because we're able to build on the learnings of the first one and reuse components. The other business stream will be to license to OEMs. Now, one of the key points that's coming out of discussions is the OEMs of intercontinental business jets. They sell high-performance, luxurious aircraft. They cannot have us encroaching on the cabin or losing out on the range. And so we're putting in some very specific plans to allow that criteria to be met. And that actually is going to be done by having a combination of Jet A and ammonia availability on board the aircraft.
Okay. Like a hybrid system.
Actually, no, hybrid that's a term used for something else. So I'm not using that here.
Okay.
It's a fuel type arrangement. Let's call it that.
Okay. Interesting.
The hybrid technology is something that we'll be looking at to improve the efficiency of the aircraft.
Okay. Interesting. And where can people find out more about all these plans that you have? Where would you send them to if they were willing to to learn more about this?
Well, I'm getting a lot of questions. I'm getting questions from university students. I'm getting questions from investors. I'm getting questions from engineers, airliners, the whole kit and caboodle. And the way they find us is through the media announcements that we make. And they appear in a variety of places. If you want to go specifically looking for some information, you can go looking for them on aviationh2.com.au.
Yes.
Or you can go look for us on LinkedIn.
Okay. Yeah, definitely. I'm gonna post the links on the show notes. And in the meantime, you're based near Sydney, right? Is that where you have your facility?
Yes. In Sydney, yeah.
Okay, very good. Well, definitely, it's a very interesting project, very unique in many ways, which I think makes it a standout in this increasingly crowded space of alternative propulsion. Yes. But yeah, that's what really caught my eye. So I will be posting all these links to the show notes so that people can research further and find out more about you guys and what you guys doing. And yeah, so wishing you all the best with
Thank you,
with this project.
I really appreciate the opportunity to speak with you.
A pleasure. Thank you so much for your time today. Before you go, and if you like this podcast, a quick reminder that it would be absolutely great if you could please give it a rating on Apple, Spotify, or whichever platform you're using, or recommend it to a friend or whomever might be interested. Thank you very much and see you soon.